Hi, this is our fifth video in Unit 5. We've been talking about the electronic structure in atoms. In this video, we're going to talk about the quantum numbers. There are four numbers that are going to describe the location of electrons in atoms. I like to think about it as an address for the electron in atoms. Okay, well, the current model that is proposed for the atom is called the quantum mechanical model of the atom. And so it was developed in the 1920s, and we know a few of the scientists. We've studied a few of them. First of all, the Werner Heisenberg and his uncertainty principle. We watched a video and we looked at that. Then we also did some calculations with de Broglie's formula, and he gave wave properties to really small particles like electrons. And so the quantum mechanical model is a wave model of electrons, and so this model was then built upon de Broglie's studies by a scientist named Schrödinger. And in his model, he came up with what we really can summarize as an electron cloud model for electrons. So he used a lot of mathematical equations that use differential calculus, and that's beyond the scope of this class. But we can learn a little bit about what he did. So Schrödinger's quantum mechanical model of the atom assumed that the electron was a standing wave around the nucleus. And this allowed only certain energy levels for the electron. And so therefore it would explain the line spectra that we see with different elements. The electron is not moving around the nucleus in circular orbits as Bohr had proposed. So how is it moving? The answer is we really don't know. This wave model gives no information about the detailed pathway of the electron. And if you remember, Heisenberg's uncertainty principle said that we can't know precisely the position and the momentum of a particle at any given time. If we know one with high probability, then we're not going to know the other one with much probability at all. Well, let's talk about what an atomic orbital is. An atomic orbital is where you would find an electron with about a 90% probability of finding an electron within this orbital. And an orbital can house no electrons, 1 electron, and a maximum of 2 electrons. What an orbital is, it's a specific wave function for the electron in the atom. And then if you square that, it will give you the probability of distribution for that electron. So electron density maps are kind of cool to look at. It's just a visualization of an orbital. So here's an electron density map, and the dark blue areas show places where there's a high probability of finding an electron. And notice that you see there's a certain shape to this orbital, and we're going to find later on that this is called an s orbital, and it's spherical in shape. And the farther you get from the nucleus, the less likely you are to find the electron. So again, an electron orbital is just a region in space where you're likely to find an electron, and it can have no more than 2 electrons per orbital. All right, well, let's get on to these quantum numbers. Now, Schrödinger had all these mathematical equations, but really it could boil down to these 4 quantum numbers for the electrons. And they're going to describe different properties of the electrons. Well, the first one's called the principal quantum number, and it has a lowercase n, and we've been talking about this for a while. And it can have values of 1, 2, 3, 4, 5, 6, and we're probably not going to go above 6 in this class. Remember that as n increases, the energy increases, and so also as n increases, the orbital is getting larger, and therefore the electron, if in that orbital with a higher n value, it's going to be spending more time away from the nucleus. All right, so the principal quantum number told us something about the energy of the electron based on its location with respect to the nucleus. Well, the angular momentum quantum number, it's a lowercase l in cursive handwriting. It has a value from 0, but it has an upper limit based on the principal quantum number of n minus 1. This quantum number is going to tell us something about the shape of our orbital. So n told us about the energy of the orbital, L is going to tell us about the shape, this region in space where we may find an electron. All right, so L is assigned letters. So first of all, let's go ahead and we just have to learn these letters. So here's L and then the letter designation. Okay, we said that L starts at 0. So if L is 0, we call it an s orbital. If L is equal to 1, it's called a p orbital. If L is equal to 2, it's a d orbital. And if L is equal to 3, and that's where we're going to stop, it's called an f orbital. Now, remember that the value of L is going to depend on what energy level you're in. So let's go ahead and start and say that we're at n is equal to 1. So we're in the lowest energy level. What are my possibility for all of my values of L? Well, L can always be 0, and in this case, that's all L can possibly be. The upper limit is n minus 1, which for our principal quantum number n is equal to 1 is 0. And so if we're in energy level 1, we'll only have one sublevel, and that's going to be an s. Let's move up in energy to energy level 2. What are my possible values for L? Well, L can have a value of 0, and you just keep going up by ones until you hit that upper limit of n minus 1. So that would be 1. So we are now in our second energy level, and we have two possible sublevels. We have S, and we have a P sublevel. All right, let's go to energy level number 3. What are our possible values for L? They would be 0, 1, and 2. So if we are in our third energy level, we could have sublevels S, P's, and D's. I hope you're seeing a pattern here. When n was equal to 1, we had one sublevel. When n was equal to 2, we had two sublevels. N is equal to 3, we had 3 sublevels. Well, let's predict what we're going to have. If n is equal to 4, we're going to have 4 different sublevels, and that would be L equal to 0, 1, 2, and 3. So when L is 0, we call it an S. When it's 1, it's called a P, 2, D, and 3, an F. There's lots of information on this slide, but first of all, realize that if you're in your first energy level, you can only have s orbitals. When you move up to n is equal to 2 in higher energy, you can have s's and p's. Not until you're in the third energy level can you have d orbitals, and the f orbitals don't come into play until you're into your fourth energy level. And so we're going to be practicing a lot with these angular momentum quantum numbers, or L. Now remember, I said that L talked a little bit about the shape. And what I want to do is to show you the shape of these S and P orbitals in this next video. Okay, so what we're going to show first is the 1s orbital, and here it comes. It's spherical in shape, and there it is. That's the 1s orbital. Well, now this is the 2s orbital. Notice it's larger, but it has the same shape. It's spherical. Here is a 2p orbital. P orbitals are dumbbell shaped, and that p orbital is going to orient itself on the x-axis. Here comes a p orbital that's going to orient itself on the y-axis, and here comes our third p orbital in energy level 2, and it's going to orient itself on the z-axis. Now notice in the second energy level, there are 3 p orbitals. Notice we didn't see any p orbitals when we were in our n is equal to 1 energy level. There are no 1p orbitals. Now, what this is a region in space where there's a high probability of finding electrons. And in any given orbital, you can have a maximum of 2 electrons. Okay, we didn't get to see d orbitals in this video, so let's go and look at another, this one has some music behind it. It's a little bit odd, but we're going to see some sp and some d orbitals. So go ahead and we'll watch this video. Maybe we'll watch this video. Here we go. Here's the s orbitals. Again, it's spherical, the s orbital. There are our 3 p orbitals, the px, py, and pz. They have that dumbbell shape to them. They're just oriented differently. And here come the first d orbital. Kind of looks like a clover leaf. So that's one d orbital. Here comes the second d orbital, oriented differently in space. Here comes our third d orbital, our fourth d orbital, and here is the fifth d orbital. So notice, we had one s orbital, we have 3 p orbitals per energy level, and we had 5 d orbitals in an energy level. There's s, there are the p's, and there are the 5 d orbitals. Okay, so let's move on. Now that we've seen the different shapes of the S, the P's, and the D's, here are the shapes of the F orbitals. And notice they just keep getting more and more complex in their shapes. But there are 7 different F orbitals. So just to review, we had 1 orientation in space, 1 S orbital for an energy level. We had 3 P's, 5 D's, and 7 F's. Okay, well those are 2 quantum numbers. We have the N, the 1, 2, 3, 4. We have the value of L, the S, P, D, and F. And now we have something called the magnetic quantum number, or M sub L. And it has a value that depends on the value of L. And it can be between L all the way through negative L. And that's going to include 0. So let's go ahead and talk about an L being equal to 0. If L is equal to 0, what kind of orbital is it? Yep, it's an S. Well, our M sub L value can be anything from negative L to positive L. Well, it's just going to be 0. Okay, let's look at L is equal to 1. So what kind of orbital is that? It's a p orbital. And what are all my possibilities of M sub L? From negative L, could be negative 1, 0, or 1. So we have 3 possible magnetic quantum numbers when L is equal to 1. Let's go to L is equal to 2. So we're talking about the d orbitals. And our values of M sub L could be negative 2, negative 1, 0, 1, and 2. Looks like we can have 5 different quantum numbers for our d orbitals. And then let's look at L is equal to 3. That was our F orbitals, and our M sub L is going to be negative 3, negative 2, negative 1, 0, 1, 2, 3, and we have 7 different F orbitals. The value of M sub L is related to the orientation in space of the orbital. And it is going to tell you the number. So we have here 7 different values of M sub L for an F orbital. So we have 7 different orbitals. And then our last quantum number is called the electron spin quantum number, and it can have a value of plus 1/2 or minus 1/2. And so what we're going to find is that we're going to be putting electrons in orbitals, and we can draw an orbital as just a line or a box. And within a box, we can represent electrons as an arrow, and we would draw one arrow going up and one arrow going down. These would be 2 electrons in the same orbital. That's the maximum that we can have in any orbital. One would have a spin quantum number of plus 1, and the other one would have a spin quantum number the first electron would have a spin quantum number of plus 1/2, and the other electron would have a spin quantum number of minus 1/2. And we're going to be just playing lots of games with these quantum numbers tomorrow. And the last thing I want you to know about is called the Pauli exclusion principle. And that states that no two electrons in any one atom will have the same set of quantum numbers. And so it's kind of like an electron social security number. No other electron in that atom will have the same set of 4 quantum numbers, and that's known as the Pauli exclusion principle. Okay, well, we'll see you tomorrow, and we're going to do lots of problems with quantum numbers, and hopefully by then you'll have it. See you then.